Okay, so we're going to continue talking about state machines, right? The state machines being one of the, if not the most important tool that we're going to have for digital design. Where when I describe a system like I want to detect a sequence of 101, these sequence detectors are kind of quintessential examples because they're super easy, right? The first example I did is the red light or the stoplight overall, and it turns out those are really complicated because they have tons of ways to make that decision and checks and balances. Well, I want to detect 101. Now, when I say detect, I mean I'm going to have some output that is 0 until I have that sequence, right? The way that I do this, that I'm going to design this, and this is true forever and ever. Anytime you go build a digital system, this is really where you're going to start, unless you're a mad person, where you're going to have some idle state. We could call this S0. I think the book tends to use S0, S1, S2, blah, blah, blah. I'm going to give them useful names because I like useful names. And then when I want to design a sequence detector, what I'm going to do is I'm going to step through the main path, right? And I know there are two different kinds of state machines, remember? We have mealy and we have more. More requires more states than mealy. The difference being mealy requires that the outputs depend on both the current state and the inputs. Whereas a more state machine requires, or the output depends only on the current state. So last time I did a mealy state machine example with the sequence detect, and it took 3 states, right? And we can do this super quick and easy. In fact, I'm gonna change this. I don't like non-descriptive state names, but I'm gonna change it because it's gonna be easier when I draw the table later. Right? And so this is saying I saw a 1, I saw a 0, and then I saw a 1 and I detect. Right? Z is my output. This is Z is 1. This is not a complete state diagram because if I wanted it to be complete, then I would say not Z, not Z, right? The inputs are on the left, the outputs are on the right. So the condition to make this move is a 1. When it does make that move, the output is not Z. It doesn't change inside of the state. So now we bounce, and now we have this 1. So you can imagine that if I have, there's 2 different versions that I might want to detect, and we have to understand, does this detect once or twice? Right? We have to make that decision because either could be true. I generally make you guys design for overlapping sequences, meaning that yes, my output Z would be 0, 0, 1, 0, 1. Right? Because it's detected twice. I have 1, 0, 1 here, 1, 0, 1 there. 2 detections. That is an overlapping sequence. All right, so let's say this is how I want to design it. That means I need to be ready to make this second detection, which means I'm not back here at state 0. So what I want is I went 1, 0, 1. Well, this state is saying that I've seen a 1. That state is I've seen a 1, right? And now, if I get a 1, 0, 1, I get a detect, and now I get it back to 0. We've deasserted the output. 0, 1. I've detected twice. Success. That's my main loop. Now it's just a matter of going back and figuring out what happens in the other cases. Well, the first one is almost always easy in that if we just, especially in sequence detector, where if we don't see the right one, we just hang out. The second one, I have this 1 coming in here. What happens if I get a 0? I go on. If I get another 1, well, this state, as we already mentioned, is I've seen a 1. Then here, I have the 1 output. What happens if I see a 0? Well, this one's a little more complicated, right? Because coming in, I saw a 0, and going out, I saw a 0. That means there's this 0 and 0. There is no 0, 0 in this sequence, so it stands to reason that I have to start over. That is now a complete and formal SM diagram, okay? You're going to have a sequence detector or something similar on the exam, I promise. If there are any questions here, let me know. I tend to use 4 or 5 numbers in the sequence for my exams. The next step then is I'm going to fix this, give myself a little bit more room. Okay, and now we can move on to the state machine table, which is where we kind of, the last thing that we did that I a little bit rushed through, right? Where the table is where we transition from something that is easy for our brains to think about to something that is easy to turn into code. Okay, this is kind of the intermediate step in making something code, where we care about our current state, our outputs, and our next state. Now our current state has 2 different representations. We have 3 states, S0, S1, S2, right? 3 states. Oh, I lied. I was going to turn this into a more state machine, but I'll do that in a little bit. Okay, these, we can't type S0 in ones and zeros because we don't have S. S is not a 0 or a 1. So I need some number of bits to represent this number, right? This name. How many bits do I need? 2 bits, yep. Because there are 3 of them. So in 2 bits, well, I'll just do it here. 0, 0, 0, 1, 1, 0, ta-da. 1, 1 is there. It's known, right? Because there are 2 bits, and I can't magically pretend this doesn't exist. So it's there. We just don't care what it's doing because hopefully we never end up there. It's worth saying, in like a more complicated system, you may want to say that like if this 1, 1 happens, then you might actually design a specific state for it because something went wrong, right? And so the example that I would like to give in this is like, so I've done radiation hard design, for example, or for FPGAs. And if an FPGA or any digital logic is in a high radiation environment like space or a particle accelerator, and one of these registers that is storing the value is hit with a high energy emission, it can flip its bit. It can change what it is against its will and end up in a bad state. So you would want to have the bad states let you know that you got there, right? So this whole state's purpose would to be send an error up the chain and be like, look, something went wrong. Fix it somehow, right? But in this case, we don't care because we're not designing for putting this in a particle accelerator or anything. So we can keep it nice and simple. And then the next state is just a matter of depending on your input. So if I is 0 or I is 1. That means this is I, I'm going to call this I. There are only 2 options, 0 or 1. You can have state machines with 2 inputs, in which case I need 4 columns. It's 0, 0, 0, 1, 1, 0, 1, 1, right? This is the simplest example, so this is where we're going to start. The way that I like to do this is because I'm scatterbrained, and I'm not going to pretend otherwise, right? And I lose track of things. So what I'm going to do is I'm going to design first with the state names, because it is highly likely, especially for me, that if I just start trying to write numbers in the next state, I'm going to mess it up. So what I'm going to do is if I'm in state 0 and I see a 0, I stay in state 0. If I'm in state 0, I see a 1, I go to state 1. If I'm in state 1, I see a 1, I stay in state 1. What I'm doing here, all I'm doing is I'm writing down the one that is stay put first because it's easy and I'm not likely to screw it up, right? So that's the 1, stay put, 1 stays put. 0 moves on to S2. If I'm in state 2, there's no stay put, so there's no point in doing it. If I go to 0, I go back to state 0. Otherwise, I go back to state 1. And then, as I mentioned, don't care, don't care. Yes?
Is it in state 2 when you see a 1, you want this one?
Yes, in state 2, if I see a 1, state 1.
I have it back.
If I see state 2 and I see a 1, I go to S1. If I see a 0, I go to S0. No, it's worth asking.
I had it backwards on my paper, so.
But right, I'm not going to doubt. Like, it's entirely possible that I messed this up, so I'm glad someone's paying attention, because I am not immune to errors, because there's a lot going on here. I beg you, these tend to be worth a lot of points, and they are the worst thing in the world to grade, so just get it right. I will like you a lot better if it's just right. And the way it ends up working is if you screw up the main sequence, you're just going to miss all the points, because it's easy, right? Main sequence is easy. Don't mess that up. All right. The output, this is mealy, so the output is determined by the mealy, but it turns out it's easy because the only time that I assert Z is true is if I'm in state 2 and the output is 1. But it's mealy, so my outputs depend on the inputs. So again, I is 0, I is 1. And then I can simplify my life by recognizing that it's in state 2, I is 1. State 2, I is 1. This is a 1. There we go. Right. Don't care's on the bottom. So this is the easiest way to write out your state diagram. Then we need to take this a step further because we know that there are zeros and ones hidden in here. Right, state 0, 0, 0, 0, 1, 0, 1, 1, 0, 0, 0, 0, 1. This is now a complete SM table, okay? SM diagram, SM table. There's one other version of this that I actually don't think we'll get into, but you should be aware of. There's a thing called SM charts that get actually a little bit more technical, and they're more the way that computer scientists think about state machines, because it turns out that even like embedded systems like microcontrollers and stuff, they use state machines too. Their state machines are treated a little bit differently, but the way we program them are very similar, okay? Now it's worth remembering that I talked about the architecture of a state machine is as such, where you need this next state decoder that says, where am I going, right? And as we know, that considers both I, the inputs, which may be a bus, right? This may have more than one value. And then it also needs to consider the current state, and the current state is held in a register that has a clock on it and gets updated from next state. So when the clock rises, the combinational logic that is next state tells what to store in the current state. The current state is literally the same thing as your accumulator in your project, which it just stores a value. In this case, it is 2 bits wide. In your project, it's 8 or 9 bits, right? In this case, it's 2 bits wide. Current state takes 2 bits. Therefore, there are 2 D flip-flops in my current state. Therefore, I can label specifically that is 2 bits. Just like this is 2 bits, right? If there's 2 in, there's going to be 2 out. D flip-flops don't make more bits for any reason. And then the last bit is the output decoder. That output being Z, that's going to be 1 bit. And the last thing that I need to do, well, second last thing to do is that my current, oh, not here, sorry. Right, my next state looks at I and current state. All right, then the next thing that we do is we remember that this is a mealy state machine because I've written the numbers here. Mealy means that the output depends on the current state and the input, so I need a forwarding path that does so. So this is the block diagram of any and all state machines that you guys will ever be asked to design in this or 3610. They're all built the same, nice and easy. This path being optional, because if you're more, it doesn't exist. Because the output decoder only depends on the current state, which makes the output decoder logic easy, right? So then the next thing we need to understand is that my next state decoder has two outputs. Okay, well, there's 2 bits. So I have 2 outputs. How many K-maps do I need to design the next state? 2, right? Because a K-map can only ever design for 1 output. So we're going to look at that and say 2. In fact, the way we're going to call it is bit 0 and bit 1 of my next state, right? And so we want to be careful, and we make sure that we know what these are going to be called. And so I can go ahead and call it B0 and B1 of my next state. I don't remember the notation that the book uses. Oh, they use Q, right? Which makes sense because it's a D flip-flop, so Q makes sense, Q0, Q1. And we need to make sure that they're different. Actually, that's a good point. The book has kind of a good idea here I actually like, because if I call this one Q, my current state bits, then I can be a little more specific and not getting in trouble later, where this is Q0. Actually, I'll do it this way, Q0, Q1, and these are D0, D1, right? Now it's a DQ flip-flop representation. So the next state bits are D until they get clocked in and become the current state, and now the output is Q. DQ flip-flop, everyone gets it? Okay, we like good names. Good names prevent us from getting ourselves in trouble. Yes?
Is it
Q, oh, Q1.
Q1?
Okay, now we need to do K-maps, right? This is why I like these examples, is because you need to understand everything about this class and to be successful at designing a state machine, because you need to understand the flip-flop, input, output. You have to be able to do K-maps. You have to understand that each output has its own combinational circuit, which means 2 or 3 or 4 K-maps, depending on how many bits you have in your state representation. So if I have 5 states that I need, so I have 5 in a sequence and I need 5 states, now I need 5 K-maps. Sorry, not 5 maps, I need 3 K-maps, because 5 states means 3 bits. Plus what I already do for my output, right? That's just for my next state decoder. The next state decoder, we draw those K-maps. And I think this is where I left off, because I know I talked about this with some students afterwards, but I didn't do this yet, right? Okay. I just want to make sure, because right, all of this is review, so I can go fast and you guys hold on to your seats and do okay. And now we've got something new, okay? Why did I draw, well, for someone that didn't stay after last time to talk with me, why did I draw this size of K-map? This is going to be, I'm going to design for, shoot, yeah, QD0. The bit D0. Why is it 3? Right, this is a 3 variable K-map.
You have 3 states, but you need 2 bits for each state, so it's going to be like you have 4 total. Like
Almost. It's the 2 bits that you're talking about, right? 2 bits that I care about, and input. So that's what I worry about, is where am I, which are the Qs, and the input. Now, it turns out there's kind of a right way and a wrong way to do these K-maps. And I don't memorize the right way. I just kind of guess and then figure out if it makes sense.
so if this was a more, then it would only be 2, right? Because it would only depend on the state, which is only 2 bits.
Then that would be true if we were doing the output decoder, but we're doing the next state logic, which still cares about, the next state still cares about the current state and the inputs. So here, we can kind of guess, right, where those go in the K-map. Do we remember K-maps, I hope, because otherwise it's going to be real rough. Q1, Q0, and now I have to be able to fill in this K-map. And I'm going to right? So don't forget to gray code it vertically as well if it's 4 inputs, but this is 3, so it's only gray coded here. Now the next thing that we need to do is figure out where things go in this K-map. Now this is going to be one of the hardest things for you to get right on your first time until you have some practice. So, but we can think about it logically. I'm looking to figure out what is D0 depending on the current state and the inputs. So it's no surprise that in the case where my state is 0, my inputs are 0, 0, 0. So 0, 0, 0 for D0 is supposed to be 0. Now, same state, 0, 0, but I is 1. So now I have 0, 0, 1. 0, 0, 1 is 1. Because, and I want to be very clear about this, D0 are those bits, the blue underlined bits. So here's what's awesome. So you can go through this, right? And go 0, 1, 0, 1, 0 is 0. Finish the K-map. Use the table, finish the K-map. Yeah.
So it's kind of backwards when you read it on the K-map, like 0, 1, and you go to I0 instead of 0, 0.
Well, yeah, so you need to keep track that this is my 0, 0 of my current state. So this is my, each column is a row of the table. However, it is possible to draw the K-map in a different way. But I don't like it because if I put I here, then it starts, I don't know, it gets a little twisty. It works, you can do it, but I like this one because once I've done the first 2 and verified that it's worked, the rest of this actually takes me like 3 seconds. And I'll show that after you guys have a moment to finish this K-map. Okay, good? All right. So you can check your work as I go through, but what I like to do, 0, 1, confirm that I'm column is each row. Now I can cheat and recognize that it's 0, 1 here. The next row is 0, 1 there, but the next row is this one, right? So we're gray coded. And then don't cares. Then we do our K-map, right? Which if you need to review, go ahead and spend the time to review, but due to class time issues, I'm just gonna point out, right? I have 4. I can make sure as long as the grouping is 2 to the n and only has 90 degree, right? Just squares or rectangles only. There we go. Then I can figure out what this expression is in circuits, right? By asking the question, what doesn't change? Well, clearly the only thing that doesn't change is I. So the D0 assignment is D0 is equal to I. That's easy, right? Well, now that we've done that, we can go do B1, the other bit, right? The bits that aren't underlined in blue. But this is the nice part. When you're in exam, once you figure this pattern out, now I just go, well, it's 0, 0, 1, 0. 0, 0, don't care. I assume. Then I go to my K-map. I recognize that, well, the only mix that I have is that guy. I can ask what doesn't change. Well, I clearly doesn't change. And then when we have this bridge is the second bit, well, the rightmost bit, which is really Q0. So then is the sum of products expression, right? But there's only one implicant. Remember this term. So that means it's only an and what doesn't change is not I, and Q0. And Q0 is a 1, so it is true. Now this next state logic block, that's what I just designed, is a block that has I coming in and just passes through, where this is now D0, and then I have an AND gate and that's my next block of logic, right? 2 circuits, one of them is trivial. The other one takes Q0 and the not I. I'm done. I built my next state. Turns out my output decoder is the same concept. Right? It's just another K-map, same layout, it's the same things because I still care about current state and I still care about I. And now when I look at it, where do I pull my zeros and ones from?
Current state and input.
Yeah, but how do I decide if the first column is a 0 or 1 for the first square?
Table on the right.
Yes, the table, right column, these zeros and ones. So we can say really quickly, there is exactly 2 don't cares and only 1, 1, which happens when we're at 1, 1, 1. Sorry. 1, 0, 1. So where is 1, 0, 1, 1, 0, 1, 1, everything else is zeros. I make that circle, my output decoder is as simple as saying Z is I, and what doesn't change is Q1, and it's a 1, so therefore 1. So that I plug that AND gate in place of this output decoder. Now you know the insides of the entire state machine. That's the whole process for designing a state machine from concept to actual circuit. Now, obviously, if we had like NAND gates like we did back in the early days of our labs, right, I would just start throwing some bubbles on these things and invert them, and then I would have a NAND gate compatible output logic. Which I will make you do, right? So you're going to end up with, like, on the exam, almost certainly something that looks a little more like a sum of products, right? Where it's going to be I like that or something. And so the parts of the question are, like the exam question, like here you guys go, is design me a circuit that detects 10101. Go detect me that circuit, for example. And then I will, part A, draw the state machine diagram for this circuit. You would draw one of these. Part 2, draw the state machine table for the circuit. There you go. Step 3, design the Q1 output of the net state logic, or sorry, D1 of the net state logic. Probably won't have you do too many of them, right? I might make you do all of them usually. Then you would go, you would draw the K-map, you circle the things, you draw the thing. Next part, part D, I guess that's what we're up to, right? Or did I do numbers? I don't remember. Would be, you've now made the circuit using the K-map. Part D is convert this to NAND gate compatible logic, and you would just go bubble, 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 no NAND gates. Ta-da. There is 20% of your final exam. Okay, any questions on this? All right, there will be homework. You'll be able to go through it. Make sure you do it. Make sure you ask questions when you never get confused, because this is also like week 1 and week 2 of 3610. So it comes back around, and then you'll run into some of this probably in 3710 as well, depending who teaches it. So it lingers, let's just say that, because this is a real world design tool that if you end up in digital design will haunt you for the rest of your life. And I joke, it's not actually haunting. I love doing state machine designs. You will do many of those in 3610 to do really cool things. You guys are very fortunate to be joining this program when you are, because the people that are older than you have gone through a rough time. There was lots of faculty turnover, and it wasn't very fun for them. We've kind of stabilized, and we're getting more and more electives ramping up over the time. So as you guys go through this program, we're getting a nice new building, not next semester, but a year from this semester. So not quite a year away, which comes with cool new labs. We have cool new courses rolling out, like a quantum computing course. I just made a sensors course. We'll have another, like a more advanced digital logic course. We have image processing, which talks about like MRIs and that kind of thing. Lots of cool stuff is coming. Lots of it requires this kind of thinking. Okay, so now we need to do the next step, right? Everything we've always done is a next step. So the next step of doing this is turning it into VHDL. It's rare these days that we're actually going to build a circuit by hand. It's not impossible. It could happen to you, but generally we're going to want to just do it at VHDL, right? It's just easier. So I'm going to have myself a cheat sheet pulled up, but I'm going to do most of this on the board. But I just want to make sure that I don't. I'm going to try and stick close to like actual code, because it's hard at first. It turns out this will eventually be the easiest type of coding that you do, and your instincts will be to build everything as a state machine because they're really easy. Okay. But it's new, okay? So state machines have memory, therefore we're going to have a process in them. And we have to think about it in terms of, I shouldn't have erased it, mealy or more. Something like that. And there's a bunch of different ways to design state machines. And you're going to be asked to do a couple different ones. I've really done the homework, because you can write different logic blocks, or you can combine it all into one. So I could have a separate next state decoder, a separate output decoder, and a separate state. Or I can start combining them. Now it turns out my favorite way of combining them is actually just building it as a more state machine and combine all of them. So when I say build it into a more state machine, remember I said more takes more states, is because I need a state whose entire job is to assert Z. Right? Not Z, not Z, not Z, is Z. Same concept, 1, 0, 1, that's my main path. Right, now I've seen a 1, I'm in state Z, I have detected it. Now I just have to deal with the next issue. If I see a 0, well then I have seen a 1 and a 0, and we go here. Or if I see a 1, it's 1, 0, 1, 1. That is seen a 1. Notice that there are no outputs, right? There's no /Z, because the output is not dependent on the input, only on the state that I'm in. Go back and fill in. This is a 0, right? If I'm not getting a 1, I stay put. This one has the 0, so if it gets a 1, he stays put, which is the same as that guy. This one has its 1 condition. Its 0, though, is 0, 0, so its 0 condition is back here. The other one I've already taken care of, my 1 and 0. This is now a complete more state machine diagram. Easy peasy, right? Once you understand mealy, mores are just the same. In a sequence detector like this, it is always just one more state, because you just need that dedicated detection state. All right, the reason I wanted to do this is because I want the first VHDL code that I want to design for you is going to be a mealy state machine, sorry, a more state machine, because they're easier. First thing that we have to do in a state machine diagram is create a state, right? So we've talked about standard logic vectors and standard logic and all of this, but clearly I need a thing called states. So I could create a standard logic vector and put 0, 0. That's awful, right? Just like how when you're doing your opcodes, I don't want you to put when 0, 0, 0, right? I don't like that. Or sorry, I guess it would be opcode equals, right? You can do this. That's not really good code when you could do when opcode equals load. And to do that, I just create a constant. The constant's name is load. It gets assigned the value of 0, 0, 0. Better code, right? We like that code. Turns out the types, we can do the same thing. So we can actually create a type that is a type of state. And the way we do that is explicitly called a numerated type, which is a data type that we list all possible values of. So the way that I do that is after the architecture before the begin, right? Which is because after the architecture before the begin is where we create things, right? We understand that at a fundamental level, right? Is after the architecture, but before it's begin is where we create things. That's where we declare components. That's where we declare signals. We declare constants, and we can make types. So, do we do that? Arc, blah, blah. I don't know why I did that. Type. I just say type, just like I say signal. And I'm going to give it a name. States. When I create states, I like to just do it all caps. It keeps it a little bit different. And then I just say is. And then once I do that, all I have to do is enumerate them or list what I want to be. So if I look here, I have S0 to S3. So I do S0, S1, S2, S3. Done. I now have a type called states that is, or that can be S0, S1, S2, or S3. Now what's cool is this also, behind the scenes, automatically makes these some sort of values. There are 4 of them, so it's going to automatically assign 2 bits to it. And it's going to optimize it so that these states are in an optimal configuration for minimal logic. We don't have to do any of that. It just happens when we go and implement it. But it's important to understand that it's doing that so we can be aware of potential problems when we go further with the design. Now, the next thing is I need a signal that can carry these states. So this is just saying that there is this type. This is like saying that there is standard logic vector. This is similar to saying use the IEEE library .numeric standard blah, blah, right? I need a signal. So what I'm going to do is write signal. Do I want to do this as current state or next state? I'm going to do next state. So my signal, my next state, this gets a little confusing, unfortunately, and I will explain why in a minute that I've decided to do it this way, because it's really important, because this still gets my junior level 3610 students, and I want to make sure this ends up clear. So I'm trying this a different way. If it falls apart, I'm sorry. This is a new way of teaching this, and I want to see how it goes. So I'm going to call it next state, just NS, right, as opposed to current state. And I'm going to start combining some things, so I don't even think I need a current state, but I'm going to create it so that you guys know it's there, okay? And then once I have that, I need to tell it its types, just like any other. But its type is the type that I just made. Right? So here, normally I would say signal NS, standard logic vector, whatever, right? But instead of standard logic vector, it's this type that I made. Don't confuse the signals that you've made with the type that you've made. They're different. And I can even assign it a default value of S0. Something that I need you to be very careful of is understanding that this does not synthesize. So when we go put it on an FPGA, it isn't going to start in S0 because you did it. This equal sign is used for simulation. Okay. The reason that this happens is VHDL actually wasn't really designed to turn into hardware. It's really just designed to simulate hardware. And then we adapted it to actually also design it. So it kind of has this weird legacy issue where you can do things that are only simulation, right? But this is still helpful for simulation. But I shouldn't need it because my reset condition should account for whatever where I want to start, right? Because it turns out that like you can just reset it and you should know everything that's going on. You should know where you are. All right. So then the next step is to build what is basically the fundamental backbone of all of your state machines, okay? And the way that we're going to do this is we're going to, after the architectures begin, and I'm going to have other signals that I'm going to use, right? But these are the new stuff, and we'll just kind of assume that the other things that I want exist. I'm going to switch colors. This red is kind of going on me. So we're going to go ahead and say, let's go begin. And I already said it takes memory, therefore it needs a, what do you put it inside of? Process. Yes, I heard it. I don't know who said it, but yes, you're right. This, remember, it's called my sensitivity list. This is the thing, the list of signals that will make this process run. All right. The reset is in my sensitivity list. That means this process can run if reset changes. That makes this an asynchronous reset because it can reset not synchronized to the clock. Unless I specify otherwise, I recommend using asynchronous reset because they are just easier to deal with in your simulation. Rather than having to synchronize them to the clock, you can just reset it however you want. It's just easier to deal with. Okay, the process is going to have a begin that I'm not going to write because I just want to make sure I don't run out of space. And it's going to start with if reset. The reason that I put reset first is because if I write it the other way, if I write if rising edge of clock, else if reset, then the rising edge of the clock will trump the reset, right? It takes over because it's first in the if statement, which is kind of problematic. Okay, so what I want is reset first so that if reset is true, nothing else happens. Okay, so if reset is 1, active high reset, more specifically an active high asynchronous reset, right? Then my signal next state is going to be S0. So if I reset, the next clock I want you to go to S0. Okay, now, else if rising edge of clock, remembering that this is, you would actually write out rising edge, I'm just shorthanding this. New term, case. Now a case is basically just an if statement, but we don't have to write as many if, else if, else if, else if. It gets really annoying, right? You can imagine that you need an else if for every single state, which is kind of awful. So we do this as a case statement, which is a little bit easier. And I just say, well, I want a case on my next state, which is only kind of true. This may get confusing, but I'm going to stick with it for now, and then I'll talk about why I've decided to do this. So in the case on the next state is, shoot, I'm really afraid this is going to confuse you guys because normally by the time I bring this up, you've seen a simulation of it. So I'm going to case on current state at the moment so that we can think about this the right way, and then I'll explain why you might do it the other way. Case on current state is. So basically it's asking the question, what is current state? And then the answer is, well, when on S0, then, right, not that word then, we do the therefore sign. And then now I can say, what does it do? This is the case. And this is nice because in this example, it's really easy where I can literally just write if I equals 0, next state equals, right, so I'm in current state, my next state, if I is 0, I want my next state to go to, this state's put, right, S0. Else, next state goes to S1. Now, I could use the else if I equals 1, but in VHDL, I always want an else, because otherwise it has this implied else don't care. Now, it turns out if you put else up here, it's fine, because it's only 0 or 1, so you have actually accounted for all possible values. But that's not quite true. If I is standard logic, why isn't that true? Put another way, why is this not accounting for all possible values of I?
It's only one bit.
In standard logic, what are the values that I can have in standard logic that you're aware of? 0, 1. Sorry, what? Well, not 0 is 1.
Yeah.
But you've seen it. You've seen the other values in your simulations. Z, U, X. Those are other values that I can put into a standard logic. So therefore, if it's 0, it goes to S0. If it's 1, it goes to S1. If it's U, don't care, I guess, right? Which means you're going to get really weird simulation results and you don't really know what's happening. So that's why it's just better to always end in the else. Now this accounts for every other possible condition. If it's 0, stays put, otherwise it's going to move on. Now we have to be careful in understanding that if I put a U in to the input, it's going to move on as though I gave it a 1, right? Which is kind of bad if we're not careful. So be aware that this creates its own issue if you don't understand what's happening. Right, this is why you need all of these fundamentals to get up to this point to understand what makes good code and what makes bad code, right? This is good code, this is fine, under the understanding that this could cause problems. But it turns out this is easy to fix. I can do better code than this once I understand that. Which is just flip it. Now, if I is 1, we go on to the next state. Otherwise, stay put. If it's not a 1, if it's a 0, if it's X, if it's undefined, no matter what happens, we're gonna, oh, I have to change that to be correct. But now we stay put. I fixed it. I made actually good code, right? The best code that I can because I have an else and I'm not gonna unexpectedly advance through my states. Guess what? This is the answer to the rest of everything pretty much, right? Because then the next thing is if I come up, I write the next when, S1, therefore, if I'm in S1, if I get a 0, then I'm going to advance. So if I equals 0, next state is going to go to S2. Otherwise, where does it need to go? It stays put.
In the case when we have to do like end case thing.
Nope. It's just each when. So I do need the end if. But then that's it. The next when is just, it just comes next. And try and line them up, right? This when would be tabbed in with this when. And this is how I like to see the tabs. This is just good coding practice, right? And if you learn Python, the tabs are actually required to make it work. So this is easy to read. I just tab in for each one layer that I go in. I've designed S1, S2, copy and repeat until I have all 4 states accounted for. This is true whether I'm currently in melee or more, right? This doesn't actually matter which kind of state machine this is. As written right now, it could be either one. But there's a trap here. I have designed this poorly at the moment because of what I was talking about earlier. So I am casing on current state, and I am assigning next state. So next state is currently changing, but I'm not evaluating next state, right? I'm not evaluating where do I go next. So I would need another process to take care of this. Or I could just change that to next state. Now, this is also confusing because I'm not actually casing on next state, right? I'm casing on the state that I'm in. So if my state is currently S0, then if I is 1, then my next state is going to go to S1. So then on the next rising edge of the clock, NS is S1, okay? Actually, let me walk this through because this is actually really important to understand how to debug your state machines, okay? Is first just think about them logically and make sure they're doing what you think they're supposed to, right? So start from reset. I push the reset button, next state is S0. So it means the next time it evaluates, it's going to evaluate S0. So when I case on next state, which is S0 on the first rising edge of clock, I go and look and say, well, if I is 1, then the next state is S1. So say I get that 1. So next state is now assigned to S1. On the next rising edge of clock, that means it's going to evaluate to S1 because that's what NS is equal to. So this works, but it's a little confusing because it looks like 2 different things are happening, right? I am updating my next state, but I'm casing on this thing I'm calling next state, which is also my current state, right? And now normally when I used to teach this as using current state here because that makes sense. And I say current state, right? If I just turn all of these to current states, now it starts to make a little bit of sense and you stop thinking that I'm a crazy person for calling this next state, right? Because I look a little weird for doing this to you at the moment. Because if I just put current state, then I evaluate the current state, which is S0, and I update current state to S1, and then on the next rising edge of clock, I evaluate the current state that I'm in, which is S1. Unfortunately, it doesn't work like that because of the way that the timing diagram works out, okay? And the timing diagram in Vivado is the entire reason that I'm listing this as next state is so that I can talk about this next part, where this is my clock that is changing states. And up until this point, I'm in S0. This is my state. This rising edge happens, and I'm going to go to S1. And let's say that I actually get the correct sequence 101. So then here I want to go to S2, right? Okay, well, here's what happens in reality. So I'm in state 0, and there's a rising edge of the clock. And what I'm going to see This is, I'm going to just call this ideal, because this is actually my current state. This is ideal current state. But what you're going to see on the CS signal, okay? So this isn't going to be here on your waveform by default. You're going to have to go into scope, objects, and then drag your state CS onto the waveform. You're familiar with that, I hope. If not, you'll need to ask me about it next lab, because you're going to need the state on your waveform to debug it. There's no other way to debug a state machine other than adding your state to the waveform. Always, always, always do that. Otherwise, debugging it is a nightmare. So you go in, you click scope, you click objects, you drag CS into your waveform. This is what it's going to plot. Well, I've reset, so I am actually going to be in S0 here. Then the rising edge of the clock happens, and it says, okay, I'm going to case on, I'm going to pretend this is current state for now, right? Case on current state, oh, I am S0, therefore, let's update to S1. So you're going to see how do I phrase this? Sorry, I may have drawn this timing diagram weird. I'll just stick and call it this, CS. You are going to see S1, okay? Now, we need to take care of these outputs. And so if I'm designing a more state machine, then the output only depends on the state that I'm in, okay? So this will help actually. So in the case when S0, after the end if, I'm gonna say Z gets assigned to 0. And here, after the end if, Z gets assigned to 0, right? Guess what? That just combined my output decoder into my current state and next state logic, okay? Right, since this is an output decoder, it's just telling my output what to do. I don't have to actually calculate all of the logic for it. I can just write what Z is supposed to be when I'm in S1, okay? Now, here's the issue. This is what you're actually going to see on your current state. S2 and S3. And so our output, based on this waveform, my output expected would be 0, 0, 0, 1, right? That's what we expect to see. I'm actually going to shift that over so we can make this a little easier. But what's going to actually happen when you run this simulation, so this is your expected out, this is your out actual, is going to be, right, I'm doing the same dash line, interesting points, things only update on the rising edge of the clock. 0, 0, 0, 0. 1. That's what you're actually going to see. Does anyone see why? Exactly, exactly. So what happens is if this is current state, right, not next state, this is current state, and the rising edge of the clock happens for S0, it updates. I'm actually going to update this just so I don't confuse anyone, right? So I'm not drawing pseudocode. I'm actually talking about what I'm actually doing, right? So CS, CS, CS. So I am in S0. The rising edge of the clock happens. It does this evaluation and assigns CS to S1. But guess what? It can't evaluate S1 until the next rising edge of the clock. So it's the next rising edge of the clock that will do this Z. So then a next clock happens and I go to S2 and the next one goes to S3. But I'm going to update my CS to S3. My current state is going to show S3 one clock cycle before I'm actually in S3. Right? So from the perspective of the code, it looks like I'm supposed to be in CS, but I'm not, right? I'm actually, the waveform I am actually showing is next state. I'm showing each, when I evaluate S0, it does the if statement and instantly updates. It's not there, it's not evaluating, it's not asserting Z as 1, for example, here. It's just saying that's where I'm going. So this is where it gets confusing, is because I am in S0. So that is my current state. But it's showing next state on my waveform because that's what's actually updating. Okay? I know this is very confusing, but be aware that's why your waveform is going to get a little bit different than you might expect if you could do this. And the way that I've done this is I have combined all 3 of my blocks. Right? The reason this is confusing is because the storage of my current state, the next state logic, and my output decoder are all inside of this one process. And guess what? This way lends itself very well, very, very well to more state machines because your outputs only depend upon the state that you're in. Okay, this does not do very well for mealy state machines because I would have to add input into the sensitivity list, but then that's going to do some really weird things. So we're going to break out that process entirely if I want to break out the output decoder, which is what we'll talk about later because we're about at end of class and I want to have enough time to pass out the exams. But keep this in mind. This is the easiest way to build it. More state machines are just easiest to build. Next time we'll talk about some more other ways of breaking it out, separating it into individual components. I'll post some homework, you'll get some practice. But these state machines, I really cannot understate the importance of this as a design concept. And this code, the nice thing is if you've been struggling with VHDL up to this point, this is different enough, it's kind of new structure, and it starts feeling a little bit more like a more traditional programming experience. Sorry, I don't know what's your name. David Rackham? Rocky? Jordan Ball? Benjamin. Let's make sure that I double up names here. Nicholas Hayward. Island. Nate Davis. Benjamin Road. Oh shoot, I got the wrong Zach. Here's Zach Lower, not Zach, whatever the other name was. Too many people get names these days. Zachary Thompson. That's you. And then another person here today. That's awesome. Almost everyone is here. I will talk a little bit about the exam. If you want to know the answers, you can talk to me. I haven't posted the answers anywhere yet. I think I did post the mean and the standard deviation into the announcement when I said it was done. This exam, what I learned was very easy for those that, how do I phrase this? Those that I saw studying here in groups actually in general did very well. People that didn't ask me any questions leading up to this exam did very poorly. So the spread is actually really large on this one. The standard deviation is a lot of points. Like a lot. I think it was 13% standard deviation or something, which is a big spread. The typical I would expect is like 6 to 8. A lot of time. The big ones that got missed, unfortunately, some of them were really easy. I did this, and I didn't even mean to, and this was kind of rude, is all of the true false questions are false. Like all of them, which I know makes you start doubting yourself, but it was an accident. And then the question number 8, right, in order. I don't want to erase. That's a signal assignment. That checked for equality, right? This is assigning something, this is asking a question, and this is the thing that we use for constants or initial values. The components, the number 9 I messed up, which is kind of funny, but you guys did very well with this, is both A and B are hold time, right? They're actually the same time period for the D relative to the clock. And then the other one is clock to Q delay. Number 10 kicked you guys' butts because I asked you to draw the timing diagram for this device. And most of you did the timing diagram for that device, right? The bubble at the clock, it makes it a falling edge. It inverts the clock. It's a falling edge device. Number 12, number 11, number 12, you guys did mostly good on. On the some of you, if you wrote something that I didn't understand, right? It's the right side of the truth table is QN01, not QN. This one, a lot of people missed that one, and they wrote things I have no idea what they were trying to communicate to me. So just be aware of that. The shift register, number 12, you guys overwhelmingly did good on. A few people missed some points there, but by and large, that one was done well. Then the next problem, which is just use 2D flip-flops. You guys got that right for the most part. It's just some of you overcomplicated it because a shift register using D flip-flops is just this. Because if I put a value here and a clock happens, it moves over here, and the next clock happens, it shifts over there. It just shifts. It's like a really simple architecture. And as your tendency is in this class, right, is you start thinking you have to do something hard, and it's actually really easy. If you did that right, though, then you just recognize the only thing the next question was supposed to be, I'm not gonna lie, this was supposed to be a freebie. This was supposed to be so easy that I was hoping everyone would get it, because the next question builds on this idea, and the only thing that you had to recognize is that I gave you this entity for a flip, right, and we need to use 2D flip-flops. The only thing I was really looking for is make sure that you had this intermediate signal. Did you connect this one to that one using the ports that I provided? That was my main check. Now, if you didn't do this right and you built something weird, then the next check was, did you build in VHDL what you drew in the previous question, right? Because that was an illustration to me what you thought you were supposed to build. And so if number 13 and number 14 didn't match, then you missed more points than if they did match, even if they're wrong, right? The devices in order. The first one is a T flip-flop that is an active low reset, right? Because boggle is the reset signal, because it says if boggle is 0, then temp goes to 0 as the output. Reset means go to 0. The next device is a D flip-flop. Should be really easy. I didn't even change the names of the signals right. It's Q and D. The next one is JK flip-flop, where J is duck and K is goose. The next one is a mux. That one, hopefully, that was supposed to be just to give it to you, right? It's a 4-input mux. And the last one is basically a question on, did you do the lab yourself or not, right? Number D, it was just a full adder. You guys should have written that code so many times that it should just be recognition. And I think like 90% of you guys got it right or something. Then the full adder, sorry, the 17 code. The errors, just real quick, the end entity should be end garage door. Line 17 is missing a semicolon. It's missing the rising edge of the clock. It's missing a then on line 26, and it's missing it uses equals instead of that on both lines 42 and 43. And then the other one that you got credit for was the ends of the else ifs. There's no else, so if you said it needs an else, that's also acceptable. Anyways, that's the exam. I'm pretty much out of time. I kind of have to run to my next class really quickly today, unfortunately. But I do have office hours throughout the week. You can email me if you have questions or if I messed up your grade versus what I wrote down and versus what I put in.
Me too. But I know if I do that, I won't come back.
That's you.
Oh, you're
And
doing
that-
Q and minus one.
Yeah, because like you can't do the same thing, right? Because you can't like say,
Yeah, I
I
get
was
it now.
just sitting here like,
T minus one, like whatever. Minus one.
you're so disappointed.
Yep, I mean, it all gets a point.
Oh, I needed.
Dave, did you right, yes? Everybody got the yes.